Okay, I think we can start it now. Is it okay for you, Karen?
Yeah, I'm good. Yeah, we can start.
Okay, I just on behalf of organizing committee of this conference, IRMAS 2021, I just welcome you all for this session. So this session is going to be the session uh, 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 session 9 of this conference, the theme of robotic manipulators. So we have around 8 papers. So we have 8 papers that is going to be presented in this session. So with us, we have the session chair, Dr. R. Tyagarajan. He is currently the postdoctoral researcher at University of California, Los Angeles, and a research scientist on the Additive Manufacturing Consortium of Concrete, USA. So before this appointment, he have been visiting faculty at IIT Tripati and IIT Madras. So he has been completed his research from IIT Madras, and before that, I am very happy to also recognize him as one of my juniors in my masters when we are studying in Madras Institute of Technology and University. His research areas are the field and service robots, advanced control system, automation, and manufacturing. So we are happy to have you in this um, forum. We are going to very happy to have you and delighted to host you for this the papers. Uh, just a few instructions for these participants. So we have to keep the time on. So I just request everyone to have this timing maintained properly. So 15 minutes per paper. That is going to be 12 minutes for presentation and 3 minutes for question and answers. So let me keep it all together. So you will be given a warning sign in every 10th minute, okay, to conclude. So I think we can start. Tyagarajan, can you give some opening remarks before starting?
Yeah, sure. First of all, thank you, Dr. Saravanan, for the warm welcome and the introduction. It is really great to be a part of this conference. I just briefly went through all the topics that are going to be discussed in this session. I'm looking forward to listening to all the presenters. And just to make sure that we are sticking to the time, I think Dr. Saravanan has already told. So let's make sure that we don't exceed this 15 minutes time and hoping for a very good session ahead. I think we can start from the first paper. Paper ID.
Yeah, I'll make the announcement.
29, sir. 29.
Yeah, paper 29. We'll start with the title Kinematic Modeling and Mapping of Kinematic Modeling and Motion Mapping of Robotic Arms.
Yes, sir. We'll start.
Anish Agarwal, right?
Yes,
Anish?
sir.
Yeah. Anish, please request you to switch on the video when you are presenting.
Yes, sir.
And also you just share. Yeah, please.
Sir, we three co-authors will be presenting simultaneously.
Yeah, good. Okay, you can just start sharing your screen.
Yes, sir.
Okay, please start.
Yes, sir. Myself and my co-authors will be presenting on the topic kinematic modeling and motion mapping of robotic arms. Robotic kinematics is important to determine the end effector position and link position of the robotic arm. It helps us to
just a request. You can minimize that view of your thing. Yeah, fine, good.
Yes, sir. Kinematics help us to map the forward as well as the inverse parameters for n degrees of freedom of robot. In a particular case, we have taken a 6 DOF robotic arm. There are various methods to implement this. The method we have used will be explained further. Here are some of the references that we have took. Peter Koch has done an extensive work in developing a MATLAB software known as Robotics Toolkit. There are also various other software such as LabVIEW, Robo Analyzer, which we have used. We have used a 6 degree of DOF hydraulic arm. It gives an accuracy of 1 mm. All the joints are revolute joints. The wrist alone has 3 degree of freedom. That is yaw, pitch, and roll. The arm is controlled by a PDCB and it requires a electronic signal given by a Arduino setup board. The feedback is taken by rotary potentiometers of 300 degrees, which gives the accuracy of 0.1 degree. The end effector is a two-state gripper that is on and off. So this is a hydraulic arm. As you can see, the first is the waist, second is the shoulder, third is elbow, and the fourth one is the wrist. This represents the human arm. Forward camera.
Good morning, sir. I'll take it from here. So the DH convention, it is used for selecting the frames and the reference for the robotic arm. So so as you can see here, the kinetic modeling is shown on the screen. So Z is taken along the axis of the joint. So from that, we can from step by step from joint from body to the every joint. So we can form a transformation and find out the final reference position. So as per that, we have determined the DH parameters. So I'll explain in brief what the DH parameters is. That link length, it is the distance between the x0 and xi and xi plus 1 along the direction of z 0. Next is the link offset, that is along the direction of z. It is measured from xi to xi plus 1. So joint angle, it is the angle by which the joints will rotate. So as you can see here, we have a SolidWorks simulation and a model of our robotic arm, as well as a physical model. So we have verified all the values both physically and from the software. So based on that, we have represented a DH parameter table. So as per the transformations, that is from 0 to 1 frame, 1 to 2 frame, we have 6 different transformations. To get the final transformation, that is in order to represent the end effector with respect to the base, we have simply have to multiply all the matrices in order to get the final transformation matrix. So which will contain a rotational matrix, a px, py, pz of the final end effector. So basically the last three, that is the last three joints, they have all their axes coincide. So in order to find the last point, suppose we take it as A. So it will be independent of theta 4, theta 5, theta 6. So the main motive is to identify theta 1, theta 2, and theta 3. So based on the figure, as we can see here, so we can, the theta 1, we can easily find out, that is px upon py upon px. So next, we can find out that theta 3 is, can I have the mouse? Theta 3 is simply pi minus this angle. So this angle we can find out by the cosine law, that is L square minus this, this length is L3, this length is L2. So L square is equal to L2 square plus L3 square plus 2L2 L3 cos phi. Let us take this angle as phi. So phi can be represented as cos inverse of L square minus L2 square minus L3 square upon 2 L2 L3. So we are, in order to get theta 3, that is pi minus phi. So we'll get pi minus cos inverse of m. So next is theta 2. Theta 2 is the addition of this angle phi 1 and angle phi 2. So angle phi 2 can be pointed out as tan inverse of pz upon d, where d is under root of py square upon px square, py square plus px square. So that's phi 2 can be taken as a tan inverse of pz upon d. Next is phi 1. So this can be taken as the extended triangle. So that is tan theta 2 is equal to L3 sine theta 3 upon L2 plus L3 cos theta 3. So to get the final theta 2, we have to simply add that is tan inverse of theta 2 plus phi 2 plus tan inverse of phi 1, that is tan inverse phi 1 plus phi 2 upon 1 minus phi 1 phi 2. So we'll get the following equation.
Hi, Arthur. It's like just a reminder, last 2 minutes. Huh?
Okay, sir. So actually, for all this is all a very tedious process calculating it analytically. So what we did was we developed a MATLAB script which would do all the calculations for us. And we used the robotics toolbox created by Peter Cork. And it has a library which allows us to create a robotic arm with the DH parameters which we have calculated. And there are two main functions in this toolbox, that is ikine and fkine, which indicate inverse kinematics and forward kinematics. So as the functions imply, they help us to calculate help us to do the calculations for inverse kinematics and forward kinematics respectively. So what we did was we developed a GUI which would integrate these functions into a single screen so that it would be very easy to use. So the methodology for using the GUI would be, first the user gives the input of the required coordinates in the text boxes, position X, position Y, position Z. And then we have a button known as inverse below the three boxes. This button is linked with the callbacks function, which has the script for inverse kinematics. And the output of this script is basically, it gives us two outputs. One is a matrix, which has six elements. And these six elements are nothing but the six joint angles of the 6 degree of freedom arm. And the second thing which it gives is a plot of the robot, which shows the represents the robot after the movement. The main aim of this GUI would be to verify the mathematical model which we have created. So once we have given the input coordinates and we have received the output angles as the in the GUI, we will provide a suitable electronic signal with a particular slope. So this will be a trial and error method. So as the hydraulic valves of our robot are proportionally controlled. So proportionally controlled, as the name signifies, they have a particular slope which is required to be given through the electric signal, that is y is equal to mx plus 3. So what we are essentially doing is we are trying to find the slope m. So after giving a particular signal, we will check if there is an error between the actual position and the required position. So this would be basically done using potentiometers. So we have potentiometers mounted on each revolute joint of our robot. And these potentiometers provide a feedback to the Arduino board. And the Arduino gives a real-time feedback of all the potentiometer readings. So we use, this is like a closed loop process. So we try to modify the slope as until we get the exact joint angles which are required. So this is the overall methodology. And after performing these tests, these are the results which we could achieve on the physical model, that is after controlling it. So the results were quite nearby, and this accuracy is enough for our model, like for our requirement. So as you can see, the potentiometer readings are around 0.4 to 0.7 away from 0.7 degrees away from the analytical or the theoretical values. So yeah, this is how we verified our physical model and the mathematical model together. Thank you.
Any questions from the audience? I think Tyagarajan, you can take over.
Yeah, I have a couple of questions here. First of all, it's a good work. Thank you for presenting it here. So, understand what is the overall idea behind developing this manipulator. Is there any specific application that you had in mind that you wanted to develop this particular robot?
Yes, sir. Actually, as we stated, the robotic arm has a gripper that is a two-state on and off gripper. So we actually wanted to develop it for various applications such as gripping or performing maintenance activities such as twisting some valves or twisting some screws. So that was our main motive behind this. So this would be basically a multi-purpose robotic arm, which could be used over a variety of applications.
Okay, got it. I think so. You have multiple applications in mind, but I think that is not being tested, or any results of that is not being presented in this work right now, right?
Yes,
we have one application that we have tested that is for the underwater oil plants. So there it will be used for connecting the pipelines between different and creating a colony under which will be used for extraction. So that was the first application, main application. But then we identified that it has more than one application. It can be used in various fields.
Okay, got it. The second question is, you told you are using potentiometer for measuring the angle, right? So,
yes.
what is the range of angle that the potentiometer can measure? Is it like a continuous rotation potentiometer, or a fixed range potentiometer? What is the potentiometer that you used?
It's a fixed range one, sir. It is 0 to 300 degrees. So
300 degrees. So, and I think somewhere you also mentioned that the resolution is around 0.1 degrees. Are you sure about that?
Yes, sir.
Actually, this data was
so
by the manufacturer. So
okay, so okay, the resolution of the potentiometer is 0.1, but ideally, when you connect the potentiometer with your Arduino essentially has the highest is 10 bits resolution when you have this ADC coming into play. So your overall resolution in terms of the measurable angle will come down. So I think it will be appropriate to present what will be the realistic value that you can actually measure, rather than just saying that, okay, this is the minimum resolution that you can achieve using the potentiometer. Because when you see the whole system as a mechatronic system, then the overall system parameters plays the major role, right? You won't. I don't think you will be able to measure it to the resolution of up to 0.1 degrees. It may be a bit lesser than that, and that may be the reason why you get the discrepancies in the angle measurements. When you presented the angles, there were some discrepancies in the measurements, right? I think that might also influence the results.
Okay, sir. Sure.
Anyways, that's all from me for this paper. We can proceed to the next.
Thank you, sir.
Okay. Any other questions? Okay, then thank you. You can stop sharing, please. We can just move on to the next paper. Next paper we have with the paper ID 38. So we have the paper with the title Development of Quadruped Walking Robot with Passive Compliance Legs using XL4005 Buck Converter. So with here we have Lee Han Wang.
Yeah, hello.
Yeah.
Can you hear me?
Yeah, we can hear you.
So the video is showing the correct slides, right?
Yeah, fine. Can you put it in full screen mode? We are seeing it in partial mode.
Huh?
I think you have to switch the screens.
Yeah.
Okay. Like that?
Yeah, fine.
Because I want to use the presenter view. So right now, is it okay?
No. Earlier it was better. Now it's going again for small. Okay, if you are convenient with it, you continue.
Okay. Never mind. So I'm from Malaysia, University Science Malaysia. So today I will talk about the development of the quadruped walking robot with passive compliance legs. using the XL4005 buck converter. So this is the contents that I will go through today. So I've designed and built an automated walking robot with 4 legs that has a closed loop feedback system. The working methods for the robot is mimicking the animal locomotion. So it is a trotting gait, and then the passive compliance is to improve the stability of the robot and also save energy. So to actuate the walking robot, we use the servo motors. So for hardware selection, I've used the Arduino Mega microcontroller to control, and then ultrasonic sensor as the sensor for the closed loop feedback system, and then 8 servo motors. 4 is less torque, and then another 4 is higher torque, and then 2 buck converters, 1 LiPo battery, and a 9-watt battery. So this is the conceptual design of the quadruped robot. So mainly the robot is 3D printed for the chassis and also the legs. This is the electronic circuit development. So as you can see, the microcontrollers will control 8 servo motors. So if we use this servo, the robot will draw very high current. So the solution to avoid the high current is to use 2 buck converter, because from calculation, the robot will draw 8.6 ampere. So if I use 2 buck converters, we will handle half of the current only, which is only 4.3. And then this is the flow chart to show the closed loop feedback system. So at the start, the robot will take the ultrasonic sensor input, and then if the platform in front is a good platform, so I have to tell you what is the bad platform. A bad platform has 2 conditions. The first one is a big obstacle in front, which can block the robot, and then a second condition is a cliff, like there is no platform in front, so it is also considered as a bad platform. So if the platform is good, the robot will continue to take the input until 5 instances. If the platform is bad, then the robot will change into a stepping mode, so the robot will not walk. If it is a good platform, then after 5 instances, the robot will change to forward mode and continue to move. The reason to add a buffer in front is to prevent the false detection of the ultrasonic sensor. This is the trotting gait. Trotting gait is faster than creeping, but also slower than another gates that the robot cannot use, because the gate is too fast, then we cannot handle. A trotting gate is like the illustration shown, which is one diagonally 1 3 and then 2 4 and then 1 3. This is the prototype of the working robot. So we can see all the circuits are mounted on the body of the robot, and then the servos is mounted above the legs. This will make the leg a lot lighter than other kind of working robot. So for the passive compliance, the legs is actually mounted with a elastic spring, which acts as the tendons of the legs. So to perform a step, because we have to walk, first we need 2 motions. The first one is swing, to swing the leg, and then another motion is to lift the legs. So to swing the leg, there's a servo to control the swing of the whole leg. You can see from the left picture. And then to lift the legs, you can see from the right image, there's a rotating wheel which can pull the nylon string and then to lift the legs. So by combining these 2 motions, the robot can perform a step. And then by controlling 4 legs, then we can control the robot to walk. And this is the video to show the closed-loop system. So the robot is walking, and then until it detects the cliff in front, then it will change to a stepping mode. And this is the wall, which considered as a back obstacle. And then this is the result. So we have conducted a simple test for the robot. The robot walked in 1 meter, and then we record the time. So the average time is 14.6 seconds to finish a 1 meter walk. And then this is the power consumption. So to calculate the maximum current, we assume when the robot is walking, there is half of the servo motors at store current, and then another half of the servo motors is at the running current. So the maximum current will be 8.58 ampere. So the power consumption, yes?
I want, yeah, last 2 minutes, huh? Just a reminder. Just a reminder.
Okay, thank you. So the power consumption of the robot is 51.77 watts. And then the theoretical speed. So theoretical speed is this value, and the slip percentage is 49.5%. And then conclusion is the robot can walk, can also turn, and then detect the platform in front. So what is the problem in the robot is it suffers from slipping. So for future work, we should equip 4 sensors on the foot to improve the knowledge about the surrounding, and then also improve the robustness of the control methods, such as machine learning and so on. And also reorganize the weight distribution of the robots. So thank you. So now is question and answer section.
Yeah, any questions from the audience? Anyone?
For cliff detection and the wall in front, right? Do you readjust the sensor, or did you readjust the ultrasonic sensor, or like other 2 sensors for that?
We only use 1 ultrasonic sensor. The ultrasonic sensor is tilted 15 degrees. So it can detect object in front and also detect the cliff.
Okay.
Yeah, any other questions from the audience? Okay, over to you, Tiara.
Yeah, thank you, Lihan Wong. It was a good presentation. So I have a quick question. So what is the role of the compliance in the leg that you have shown? I understand that it is not a compliance which aids the actuator as such. It doesn't act as a compliant actuator. But I am a bit confused of the role of this compliance in the leg. Can you please explain the role of the compliance?
So it has 2 purposes. The first one is to improve stability, because if the whole leg is very stiff, when the robot is walking, there will have a reaction force to the robot. So it's more prone to tip over. So with the passive compliance, it will dampen the oscillation. And then another reason is to save energy. But the energy is not safe during the walking, but in the ideal mode. If the robot is just standing there because of the spring, so the robot can stand without using any energy.
Okay, so a connected question with this. What is the stiffness of the spring that you have used?
Because when designing the robot, we didn't calculate for the K. So the K is added until the robot can stand up. I mean, when you add the spring, the leg is stiff enough to hold the whole robot without falling.
Okay, what is the weight of the robot as of now?
1.3 kg with all the batteries holding. And then the size should be about A4 paper.
Okay, is the compliance between the between the opposite links of the parallel mechanism that you have in the leg. Because otherwise you will have the whole load getting transmitted to the servo motor. And when it goes to the servo motor, it cannot take the varying positions, right? You can command a position and it will always set to that position. Is the compliance between the two links of the parallel mechanism of your leg?
Yes. What is your question?
Okay, never mind. Leave it. That's fine.
Okay.
Okay. And the second question is, you talked about the speed of the robot. I understand that the speed is majorly commanded by the speed of the servo motor that you have.
Yes.
So is it really the speed of the motor that limits the speed of the robot right now, or is there any limit from the mechanism as such?
Because I'm using the closed loop feedback system, right? So to improve the speed, then I have to improve the amplitude of the swing. So if the step is too big, then it will easily fall off the cliff.
Okay. Okay. So the mechanism as such has some limitations.
Yeah.
It is not commanded by the speed of the motor. All right. This is all from me.
Okay, thank you.
Dr. Saravanan, we can proceed to the next.
So,
yeah, any other questions for Lee Han-Won? Okay, then thank you, Lee Han-Won. Okay, we can move on to the next presentation. Yeah. So next presentation, we have paper ID 39. So that is going to be a design of Hawkin linkage-based walking mechanism with MPU 6050 IMU as navigation sensor. So Koon Ron Hoi, are you here? Or any other authors of that paper is here?
I'm Afdal. I will represent the Oikon Ren.
Okay, fine.
Okay.
Yeah, please, you can start sharing.
Cheers. Can you see the screen?
Yeah, fine. Good.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to the audience in this meeting. First of all, I would like to thank the organizer for giving me such an opportunity to present our project. Before we proceed, I will like to introduce myself. I am Afdal from UC Science Malaysia. Okay, our project title is design of linkage based walking robot with MPU 6050 as navigation sensor. Next, this is the content for the presentation, which include introduction, methodology, results, discussion, conclusion, and future work. Okay. The main aim of this project, it was to design and build an automated walking robot with 4 legs that has a closed loop feedback system. For the walking methods, we choose animal locomotion as the walking methods, and for the linkage, we choose Hawkin linkage because it is able to convert the rotational motion of a DC motor to approximately linear motion. The DC motors is implement into the walking robot. Okay. Next, for the methodology, I will start with the hardware selection. First, we choose Arduino Mega as a microcontroller. MPU 6050 initial measurement unit as a navigation sensor for this robot to walk in a straight line. Infrared sensor as a digital sensor. The function, the geared DC motor with Hall effect encoder. L298N motor driver is used to supply the voltage to DC motors according to signal received, and the 8118-650 rechargeable batteries to provide nominal voltage of equivalent of 11.1 volt to the robot. Okay. Next is our conception design for this working robot. Its dimension is 300 mm times 302 mm times 140 mm. Okay. Okay. For the electric circuit development, MPU 6050 was used as a navigation sensor for this robot to walk in a straight line regardless disturbance of environment and power supply to it. The raw data from MPU 6050 was computed to get your value of robot before it started to move and during its travel. Okay. For the IR sensor, is a digital sensor. It will send a signal of 0 volt when triggered by something, and send signal 5 volt when there is nothing approach it. The analog input is used with IR sensor so that it can filter out noise signal from environment. The 18650 LiPo batteries is used to provide nominal voltage to the robot. If the batteries were fully charged, their combined output signal will be 12.6 volts. This output voltage is connected to VIN pin of Arduino Mega and L298N motor driver to power up them. Okay. The L298N motor driver is a dual channel motor driver with peak current of 2 ampere. It will supply the voltage equivalent to 12.6 volt of DC voltage to DC motors according to signal received. For the DC motor, we use DC SPG 30E-150K with rated speed 26 RPM and torque of 588 milliNewton meter. It comes with a Hall effect encoder in its rear part that used to compute the actual speed of rotation of motor. Okay. For the software development, first, for the software development, it consists of 5 user-defined functions, which are RPM, calculate, get your, forward, stop, and the PID motor. The source code start with a variable declaration and setup, consisted of P controller setup, encoder setup, gyro sensor setup, and pin mode setup. Then
I have still just a reminder, last 3 minutes.
Okay. Thank you. Okay. After done the program declaration, the program first will enter false statement because stable value was initialized as false during variable declaration phase. Then the reading from IR sensor will taken and used to make the following statement decision. If IR less than 100, threshold value will increase by 1. So this process will continue until threshold values equal to 7. Then only robot will start to move. Next, the program will execute true statement because stable variable was true during this time. Motor forward moving direction setup will be done in forward function, and P controller will start to compute the PWM value for enable pins of 8298N motor driver. The robot will move in a straight line according to your angle that safe during starting of the robot. In order to stop the robot from moving, the same IR sensor is used to stop the DC motors from continue to rotate. IR sensor has to be triggered so that the robot will stop. Then the robot will reset to its condition, which waiting for trigger signal from IR sensor to start it. Okay. This is a software development for P controller. The P controller is named as a PID motor function. The function is executed during moving of this robot. We will call get your function to compute a set point for left and right motor speed PID. It will compute the PWM value for left and right motor enablers, and analog right compute PWM values to enable pins of left and right motors. Okay. This is our prototype of this robot. If the MPU 6050 approach some obstacle, it will give the microcontroller to set for the legs to turn left or right, depends on the obstacle. Okay. For the speed of the robot, the average walking speed of this robot was 2.53 meter per minute. This is less than the theoretical value speed due to an uneven working surface, time taken in transient response, deviation of robot heading, and time taken for adjustment. Okay. The power consumption. The power consumption is measured by measuring its input current. In normal condition, the current measured is 0.56 ampere with fully charged batteries. But in condition that motor need to produce large torque, its input current will increase up to 1.3 ampere. So the estimated power consumption is calculated from multiplication of input voltage and input current, which are 12.60 volt and 0.46 ampere. So the estimated power consumption is about 5.8 watt. The conclusion, as can we conclude from this project, the robot can walk, detect obstacles, and avoid the obstacle in a smooth sequence. The robot can read just back its pace when the robot is unable to walk due to the same phase of legs. The problems we face is suffers from slipping, and sometimes the nut that used to build the joint loosen frequently. So for the future work, we will replace current motors with higher power to increase the travel speed. We will equip the robot with auto lighting system, as our main aim for this robot is to used in mining industries. The MPU 6050 will replace with MPU 9250, which add magnetometer in 3 axes. So that's all from me. Thank you.
Yeah, any questions from the audience? Okay, over to you, Vidya.
Thank you for the presentation. So I have a quick question. There is a specific emphasis on MPU 6050 in your presentation, even in the title it is mentioned. Is there any specific reason you went for this? Because there are a lot of other options available. Is there any specific reason that you chose this?
Why we choose the MPU 6050?
Yes.
Because
do you have any answer for that?
Where?
After, are you there?
Yes.
Okay, fine. I think he don't have an answer. You can go for next question.
Okay, that's fine. So I have another question, which is, so you also mentioned about the PID controller in your system.
Okay.
Is the PID algorithm implemented inside Arduino, or is it a part of the motor itself? Does the motor itself has a PID?
We implement the P controller in the Arduino.
You implemented it is just a P controller, is it?
Yes.
So did you see any steady state error when you implemented this?
We implement the P controller because.
No, my question is, when you implemented this, when you will have the actual commanded yaw and the yaw that is happening at that moment, right? So did you see any steady state error? Because I see the system as a non-linear system, at least with respect to yaw. And I would definitely expect some kind of a steady state error in this. Did you see anything of that sort?
No.
Okay. All right. Thank you. I don't have any other questions.
Okay. Thank you, Doctor.
Any other questions for Abdul? Okay, then thank you, Abdul.
Okay, thank you.
We can go for the next paper. So next paper we have paper ID 58. The title of the paper is Development of... I think you can mute yourself, please. Abdul, please mute yourself.
Okay, sorry.
Okay. So we have next paper of paper ID 58. We have the title Development of Bridge and Lever Type Compact Complaint Mechanism for Micro Positioning Systems. So it's going to be presented by Parag Marathe. Are you here?
Yes, sir.
Yeah, fine. I think you can start here.
Okay, respected all. Myself, Parag Marathe, going to present my work on the development of a bridge and the lever type of compact compliant mechanism for micro-positioning system. And the co-authors are my guide and the mentors, Dr. Sudhit Pardeshi and Dr. Bhagyesh Deshmukh. And the paper ID is 58. So first of all, what is compliant mechanism? So generally compliant mechanism is a monolithic flexible structure.
Parag, okay, can you make the mic a little bit near to you? We are hearing some distortions when you speak.
Okay, actually, sir, I am in hospital. That's why little bit is there. Okay, now my voice is properly audible.
It's clear. Please.
Okay, what is compliant mechanism? It is a monolithic flexible structure where the elastic deformation of the elements generally used to transmit the force, and it delivers the motion and force or energy due to an input actuation provided to the link. Generally, the benefits of the compliance are they are reduces or eliminate the backlash, and there is no frictions because there is no joining parts or assembled parts are there. Because of that, there is a smooth and the continuous displacement. Also, it is an we can get infinite resolutions through the compliant mechanism. It reduces there is no lubrications is required, and it also improves a precision and the reliability of the system, and the miniaturization of the components is also there because of the compliant mechanism. Here are the some relevant literature which I did. So I took that references that Yang Li generally developed a structured materials from the compliant mechanisms he developed using the aluminum material and having the size of about 140 by 140 by 7 mm size of the mechanism, and this mechanism delivers the maximum displacement at the output is around a 64 microns, and the amplification achieved because of that mechanism. When what is the amplification is whatever the input force we have or input displacement is there, and that input displacement amplified at the output stage. So that will be the up to the 3.7 amplification is achieved. Similarly, there is a Rico, that is a researcher designed again a compact type of system and having a dimensions. I'm always using the compact word because whatever the system developed, that is also the compact. So I use, so the size was 154.2 mm, 80 mm, and 3 mm, and use the material that is a polyamide material, and it generally a beams type of a structure is there used for the gripping purpose, and delivers the displacement up to 8.5 mm, and the amplification achieved is only up to the 4.6. Again, there is a few researchers who developed, that is a China, and having a mechanism size is about 110 mm by 150 mm by 5 mm, and made up from the acrylic glass, and delivers the maximum output around in a mm, and achieved the ratio is up to a highest ratio, but the size of the mechanism also the larger one. Then the Lee, who developed a mechanism from the aluminum material, and the overall dimensions are a little bit a compact one than the previous mechanisms, and the whatever the maximum displacement achieved is around a 15 microns, and amplification is 3.7. And whatever the development I did for the mechanisms, so I all these this some literature, that 4 generally are literatures used for the presentation. In the 4 literatures, there are 2 literatures are based on the breech type of the mechanisms, and the 2 are based on the lever based mechanisms. So I used develop the mechanism, the combination of the both, that is a breech as well as the lever type, and based on that my applications. So I developed an objectives that are the design and developed a compact size, a compliant mechanism for the linear displacement application. And the second objective is to enhance the amplification ratio, so that providing a small input, I need to get a larger output. So this is the a newly developed mechanism. So this is a mechanism. Here I used a lever type of system, and here is the breech type of system. This one is the motion stage, and here is the cantilever type of a system, where we are providing a force, and that particular force will move the motion stage and amplifies the displacement. So for that modeling purpose, I used pseudo-rigid body model, that is the PRBM model. So in PRBM model, generally whatever the flexure hinges are there, so these are the flexure hinges. So it gives an deformation. So that particular flexure hinges in PRBM converted into the equivalent stiffness of the torsional spring. So whatever the stiffness of the hinge is there, that particular stiffness hinges are replaced with that springs, that is torsional springs, and that springs using the PRBM model developed the stiffness of a whole mechanism. So this is the second diagram is showing the PRBM of a compact amplified compliant mechanism. So as per the literatures, generally or in all the literature, they used circular flexure hinges. So here the same right circular hinges are used because the circular hinges are gives the more stiffness as well as carries the more load. The compliance ratio generally for the right circular hinges generally depends on the hinge neck thickness. So whatever the neck thickness is there, so this thickness and the radius of a flexure hinge, that is a R. So here R, so you can place this is an R also. So hence that ratio, that is a T by R ratio, for the manufacturing point of view is considered to be 0.5. If suppose we go with the less ratio, then there is a little bit difficult in a manufacturer, more highly precise manufacturing systems is required. So that's why for manufacturing point of view, our ratio is considered to be an 5.5. And the general stiffness of a circular hinge through the literature is considered to be K. That is the stiffness of the spring, that is circular hinge. So where the W is a mechanism thickness, so that is the overall thickness of the plate from which we are cutting out the mechanism. Then R is the flexure hinge radius, and T is the notch thickness.
Just a reminder, last 3 minutes.
Okay, so here then we calculated through the equations, that is the whatever the force input and the displacement input. So after that, that particular model is now optimized. So as the lever is going to be optimized and provided as little bit stiffness or about the bending of the lever. So the particular diagram is showing that when the maximum force is applied to that particular mechanism is 50 Newton, and that particular 50 Newtons gives me and around 26 micron, 26.5 microns of the displacement at the output stage of the mechanism, and the input, that is only the 50 Newton force is provided. That as it is a linear system, so also need to test about the what is the displacement the provided by the mechanism in the parasitic. That motion is called as a parasitic error motions. So that parasitic error motions, that is in the y directions, I got a 0.06 micron, so that negligible. And also in the z direction, the displacement I got, that is an 0.005 micron in a, that is the displacement of the moving cell. So all both the in both the, that is parasitic error motions, there are the negligible ones. So the overall stress at the force, that is will be the around achieved, that is a 72 megapascal. So here is the block diagram of a setup, that is an actuator they are placed actuating the or providing the input force, the load cell for measuring the amount of the force, the mechanism is placed in between, and a gauge is used to check out the the output displacement, and all this data is transferred to the display. The material used is a plain carbon steel. So these are the properties of the material. So from that data, plotted the plots, graph is plotted, and to the graph, it has been observed that error in the experimentation and the simulation. So the error is achieved up to the 60% error, and which is below than the 10%, which is in the acceptable range. So what will be the results after all? So the maximum displacement in the desired direction is around 26.5 microns when the input force is applied at a 50 Newton. The parasitic errors achieved, that is a 0.06 microns in Y and 0.005 microns in Z directions. And the stresses in the mechanisms, they are developed around 72 megapascal, which are the less than the yield stress value of the material. So the material will be the safe at a 50 Newton. So the ratio achieved, geometric amplification ratio achieved with the simulation is a 7.2 by the simulation, and 6.5 I got to the simulation. The overall size of the mechanism is less. That's why I said it is an 50 compact size. So that is the overall size is 70 mm by 50 mm by 1.2 mm. So it is called as a compact. So whatever the variations, that is around 6%, and that variation is occurs due to the material structures and the error associated in building the setup for the experimentation. That is the alignment error and the random error. Also, the errors associated with the instruments are also, because of that, the error may cause. Now the conclusion, stress level is within the limit, and whatever the FEA results, they are in close range with the experimental results, and the properties, the advantages, that is the bridge type or bridge and the lever type mechanisms, the combinations are achieved and compiles the characteristics of both the mechanisms and forms the stiff and the compact sized mechanism. And such mechanisms can be used in electric switches and achieve the multiple connections. Also, that particular mechanisms are developed only for the biomedical devices where there is a precise injecting systems are required. So for that purpose, that particular mechanism is developed, and little bit work is going on in developing that particular product. These are some references used. Thank you all. If I'm, hello. Hello.
Dr. Savanagumar, I think you are not audible here.
Hello.
Hey, am I audible now?
Yeah.
Yeah, fine. So any questions for Parag? Anyone from the audience? Okay, over to you, Tyagarajan.
Yeah, I have some questions. Are you worried about hysteresis in this? Compliance mechanisms usually have hysteresis, and it also depends on the material that you use. I think you are using carbon steel, right?
Carbon steel, yes.
And I expect some hysteresis in this. Are you worried about hysteresis in your work?
Right now, not. I not faced any problem.
Do you expect some hysteresis in this?
Little bit. If suppose there is a static structures are there, because of that, there may not worry. Right now, I'm not faced any about that hysteresis.
Okay.
Consider.
And the second question is, you talked about, so right now it is displacement amplification that you discussed. Yes. Are you also concentrating on force amplification? Because I see the skeleton looks like there will be a force amplification also. Did you do any analysis of force amplification with your mechanism?
No, sir, no force amplification is done, because whatever the force, if suppose I'm planning to go amplification, then there is a problem may arises about that bending of the rigid structures may be there. So generally the compliant mechanisms are whatever the I am using for the application purpose. So for that particular applications, I'm need only to amplify, as I'm using the that is piezo actuators as an input device. or input force. So for that, because of that, I need to go with only the displacement amplification.
Okay, I think it may be worthwhile to see also if there is any force amplification. I mean, of course, it depends on the application that you're working with, but I expect some kind of a force amplification in the mechanism, that at least in the skeleton that you showed. And I have another quick question. You also mentioned about optimized structure. So what is it optimized for?
Actually, I optimize that particular lever. Generally, that particular that lever is there. That lever I have optimized as the lever is going for the bending operation. It goes under the bending because of the application of the force. So I optimize that particular lever only for that mechanism.
So optimization, you mean you optimize the dimensions of the
yes,
links that you used, or
yes,
geometric optimization?
Geometric, yes, geometric optimization.
So, okay, what is the objective? Is it to increase the displacement, or what is the objective?
Yeah, objective is increase the displacement.
Okay, so that also depends on what is the. You also talked about the hinge dimensions, right? R, T, and all. So are those chosen to be a fixed value, or these things are also parameters in the optimization algorithm?
Yes, I did the optimizations of these parameters using the Taguchi, and through the Taguchi analysis and yes, design of action DOE has been done, and from that I just picked out that particular values of that dimensions, that are the what is that value of the T and W, and what is the radius, that is R of that particular hinge. From that I picked out I used L18 array for that.
Okay. Yeah, this is all from Dr. Sharma. I think we can proceed to the next paper. Thank you.
Yeah, I think any other questions? Okay, I think no more. Fine, thank you. We can move to the next presentation. So next presentation we have with us paper ID 80. So the title of the article is Development of a Small Scale Cartesian Coordinate Farming Robot with Deep Learning Based Weed Detection. So we have with us Raj Lakshmi TS. Madam, I think you can start projecting yourself.
Okay, sir. Is my screen visible?
Your screen is visible, madam, but your voice is not that high. You can just make sure that mic is near your mouth.
Yes, sir.
Okay.
Okay, sir. The paper titled is Development of a Small Scale Cartesian Coordinate Farming Robot with Deep Learning Based Weed Detection. And in this paper, what has been done is that we have developed an automated and scalable Cartesian coordinate based farming or gardening management system, wherein seeds are being planted in precise location and pattern, and in fact, watering can be done for each of the plant at particular interval, depending upon the type of the plant that has been seeded, and also based upon the soil humidity and weather conditions. And also in case of any weeds that has been located near those, we can remove those weeds at the infant stage itself using a feed from the camera and using the deep learning. So this system, how it is useful is that it actually encourages people to go in for small scale farming. Say, for example, even as a terrace farming, we can go in for where we have very small area where a human intervention is not of a major concern, and we can go in for such a system. And moreover, say, for example, overwatering can lead to a plant getting damaged, or even wastage of water is a problem. So all these factors can be considered when we go in for such a system. If you look at the existing system, we find that we do have gardeners who go in for regular checking of the plants that they have planted, or looking in for weeds, or they need to water in. And in fact, if they need to measure anything using a sensor, the thing is that they have to either manually go to each and every point to measure the sensor, or we need to place in the sensor at all each and every location, which is also going to increase the cost factor. So in our proposed system, what it is that we have developed a machine which will be able to take care of the such that the growth volume of the plants is around 990 by 745, and it has a fixed bed gantry system where the work bed actually stays stationary. It's only the X, Y, and the Z axis that we are planning to move over that, where the Z axis actually consists of the tool holder. So we can have any number of tools that could be attached to that for this purpose. And the Arduino code functions are actually scripted in order to read the G code, which will help to enable the positioning of the access motors at the required locations. So if you look at this, this is our CAD model, and this is the system that we devised, and these are the tool base, and these are the seal holders. So this is the Z-axis, which is actually movable, and this Z-axis actually has a point wherein tools can be attached to it in a fixed manner. So this is a tool which is used for the purpose of putting in the holes wherein the seeds could be dropped. And on this other side, we have the humidity sensor. So what it is that if this tool is not in use at that particular time, it stays in this 90-degree position. And if suppose the seeding has to be done, then this moves into a 0-degree rotation, wherein it will punch in the holes. And if suppose the watering has to be done, then it's the humidity sensor has to be checked. So it moves into a 180-degree position in order to check it. At other stages, it remains in this 90 degrees. These other tool base, they have the seeding tool, they have the watering tool and the weeding tool that are being fixed into this. And these are the seed holders. The seed holders can have any variety of seeds of any different sizes. If you look at this seed tool, the seed tool will have on one end, it will have a vacuum pump which will be able to suck in the tools, and also it will have a filter at the end, so that the seeds that are being sucked in doesn't reach into the system. And these, depending upon the type of the seed that is required, it will pick up the particular seeds. And if it is a watering case, these watering case, the watering tool is attached to that of the water primer and the flow sensor, so that we will be able to restrict on the amount of water that needs to be poured. And this watering, it depends upon the type of the plant, which will be added in as a lookup table, which will indicate for which type of plant how much is the water level and what is the particular interval during which the water is supposed to be given. And then the weeding tool. The purpose of the weeding tool is it will just plunge in the weed into the soil. And for our system, these are for a rough estimate, this was all the position coordinates were considered, and these are the positions at which the plants were actually, the seeds were actually planted. So these are the positions for which watering was done as a testing stage, and the weedings were detected. So if you look at the communication protocol, these are the commands that are used in order for the so that we'll be able to position the machine to a particular position, or say suppose we want to perform any task, then we'll be able to perform that. So the command is being read, and the Arduino code, the first 3 characters are read to verify whether it is a G code or not. And in the G code itself, the position of the X, Y, and Z axis are being determined. And the sub operation is read from that. And the strings are converted to integers, which will indicate where to which position the tool is supposed to move. And the Z-axis is supposed to move. And accordingly, the axis motor will turn and move, and it will take you to that position. And the substring command is executed, and it will move on to the next command. It will wait on for the next command. In the case of the substring command execution, what will happen is once it finds in as a substring command that has come in, all the tools will be entering into the home axis, and then it will verify whether it is seeding or watering or weeding. If suppose it is a seeding, it will determine what is the kind of the seed, and it will pick up the seed tool and it will insert the tool nozzle and switch on the vacuum pump, and it will get in the seeds and move to that particular position, and then it will insert the nozzle into the soil and drop in the seeds, and in the meantime the hole would have been plunged in by the hole tool, and the pump would be switched off and the tool will be waiting there in order to wait for the next command. If suppose if it is a watering command, then depending upon the type of the plant, it will pick up the it will pick up the tool and watering tool, and depending upon the type of the plant, it will switch on and switch off for a particular. The duration depends upon the type of the watering plant. And if suppose it is a weed, it will plunge in the weed in order to remove the weeds from it. So for the purpose of weed detection, how the process took place was, we planted the seeds, and at each different stages of the growth of the seed, the images were captured, and the data that we acquired was augmented in order to create more amount of images, and each of these images were annotated. For each of the type of the plant that we considered, we created almost 750 images for the purpose of training and 150 images for validation, almost 900 images, and training was done through YOLO. And once the training was done using these parameters: the batch size, the image size, and the momentum, and decay and the learning rate. And once the training was done, this application was put into real time, when the real time images were captured at 2 different locations, so that they'll be able to capture the whole field. And this was tested again on YOLO, and the output was a confidence score, which was tested if it was greater than a certain threshold level, for example 0.8. If suppose if it was greater than 0.8 threshold, then whatever was detected was considered as a plant, and if not, whatever is considered as a weed. And once it is a weed, then the position of the weed is found as based upon the where the position is. It was converted into the position of the weeder, and the position was sent in, and the weeder tool will move to that particular location. So these are the sample images.
Can you conclude it, ma'am? Last 2 minutes.
Yes, sir. It's almost doing it, sir. So these are the plant data images, and these are the annotated labels, and these are the type of the plants that we considered for the purpose of growth. And this is the network output that we obtained. So find that these are detected as the plants, and these are detected as the weeds, and these are the training loss with reference to the iterations. Find that the training loss has reduced after certain iterations, and at the same time the accuracy can be found to increase. And as of the future of this work can be considered, we can either increase on the X and Y axis, or what we can do is we can multiplex more machines, so that we can have each of these machines for a particular small area of land, or we can in planning to incorporate more number of tools as well, and we can establish the setup with reference to a solar energy level, and planning it for a mobile app, so that this app can be checked. The user can check on the status of the plants at any place of his comfort. And these are the references. Thank you, sir.
Yeah, any questions from the audience? Okay, over to you, Tyagarajan.
Thank you for the presentation, ma'am. So I have a couple of questions. Yes, so is it a functional robotic system that you have, or is it just a prototype that you have right now, and you just tested the deep learning part?
It is a prototype that but it was a developed system, sir. It is up and running. It's working actually.
Okay, so in that case, I didn't quite understand why did you go for G-code? Did you have any controller which is conventionally used for any 3D printing setup?
Yes, sir. Some of the parts were done for 3D printing actually.
Okay, so you just are borrowing the libraries from the 3D printing setup to position the gantry system.
Yes, sir.
Okay, so in that case, are you modifying anything to specifically suit for your own application? Because I saw some protocol being used, based on some characters, you decide whether to move in a particular direction or something. So is it a layer of code which is acting on top of the gantry's motion, or how is it?
Yes, sir. Actually, these scripts we had to design by ourselves, because we wanted to have our own hands-off experience on those. So it was actually our own codes that we incorporated in it.
Okay, because it looks like it is a complication, like going around this stuff. Because It is quite straightforward. I expect that you are using stepper motors for positioning, right?
Yes, sir. Yes, sir.
And you have a standard protocol that is, yeah, and you have a standard protocol that you want to follow. I think if you remove that 3D printing controller, it might be quite easy for you to directly implement. Anyway, that is your decision. And the question that I had is there any specific modification that you did to the YOLO library?
No, sir. It was there was no modification done. It was
okay. So you just directly.
Yes, it was just a
and how did you choose the parameters of the model? Is there any protocol that you followed there?
No, sir. It was a pre-trained model, so it was the same parameters as of.
Okay.
Yes, sir.
Okay. So you just gave the training set and just trained the model, and
yes, sir.
And because it is a pre-trained model.
Yes, sir.
Okay.
Actually, it took time for us in order to grow the plans because for each and every stage we had to take the images. So that was the difficult part actually with reference to the deep learning part was concerned. Because at each stage we may get a weed, so the system needs to detect that it is a weed or it is a plant. So data was the main factor with reference to the PD.
Okay. Okay. Thank you for the answers. I think that's it from me, Doctor.
Yeah. Any other questions, sir? Okay, thank you, madam. We'll move on to the next paper. So next paper we have with us, so we paper ID 82. So the topic is development of Theo-Jason inspired all-terrain quadruped mini mobile robot. So here is going to be Harihul Hadi Rosli.
Yes, sir.
Yeah, I think Harihul. Okay. I'm not seeing your name here.
Yeah, I cannot share the screen right now.
Yeah, Harihul Hadi. Okay, I made a co-host. Yeah, now you can start share.
Okay. Okay, can you see my screen right now?
Yeah, it's visible.
Okay, hear me clearly, right? Okay, so I'll present. Okay, so first of all, I would like to thank the organizer for giving me the opportunity to present this paper. So my name is Hadi Rosli from University of Science Malaysia. So today I'll be presenting the paper on development of Theo Jensen inspired all-terrain quadruped mini mobile robot. So the aim of this paper is to design and build an automated quadruped walking robot that has a closed loop feedback system. So the walking methods for the robot will mimic an insect locomotion, and more precisely a quadruped animal locomotion. Quadrupedal locomotion means that it will walk on 4 legs. And the type of locomotion chosen is Theo Jensen's linkage system. So in order to move this linkage system, we will implement DC motor with encoders into the system. So this is the hardware selection for this robot. The main controller is the Arduino Mega microcontroller, which will control the whole system of the robot, and an IR sensor module will be used to enable the robot to perceive its surrounding, and the DC motor driver will be used to drive two 12-volt DC motor with encoders. And the whole system is powered by 3.7 volt 4200 milliamp lithium ion battery, which is in 3 quantity, and 2 button switches. These button switches will be explained later on. So on the conceptual design, so for this Theo Jensen's linkage system, we took the measurement of the Theo Jensen's linkage system itself, because it is a proven measurement, and it will provide 1 degree of freedom, which will enable the robot to move either forward or backwards. So for increasing the stability of the robot, we have designed it symmetrically so that it has a larger surface area on the foot, as we can see on the right side image. And continue on to the electronic circuit development. So this is the circuit of the whole system, which is controlled by the Arduino Mega microcontroller. And this is the IR sensor, which provides digital signal to enable the robot to detect the obstacle within 8 centimeters. So the microcontroller is also connected to the motor driver. So this motor driver will control both the right side and the left side of the legs of the robot. So one motor will control one pair of legs, which is 2 legs. So this is powered by 3 lithium-ion battery and these 2 switches. So this is the software development part of the robot. So this is the algorithm we use. So before to start the robot, you press the green button. So once the green button is pressed, the system will stop both motors if it is moving. So when it is stopped, we'll press the red button, which will initialize the location of the robot by setting both encoders to the reading of 0. So which we will know the position will be, one side will be 6 o'clock position and the other side will be 12 o'clock position. So the reason why we using out of phase position for the motors is because the linkage system itself must be in out of phase, or if it's not in out of phase, then the robot will be unstable. So once the initialization process has finished, then both DC motor will continue to rotate. So if an obstacle is detected, then a set of procedures will be done to avoid the obstacle. So what is the procedure? So the robot will reverse itself until the encoders read the reading of 1600, and then one side of the robot will reverse itself. So in this case, we chosen the left motor. So once it's completed 4 rotation, which is equivalent to 90-degree turn, then the left encoder will be set into before turning. So after finishing the movement, then it will check again with the IR sensor whether it is obstacle. So if there's no obstacle, then it will continue on walking. So the closed loop feedback system of this robot is the encoders of the motor. So both motors will give out the readings continuously to the Arduino. So in case of one side, which is the an example is the right side encoder reading is higher than the left side, then the driver will slow down the right side of the motor so that both encoders are giving out the same reading. So once both are same reading, then it will continue running as normal. So this is the prototype of the robot. So as you can see, this, for example, is the left side of the robot, which is in the 6 o'clock position. So on the right side, it must be on the 12 o'clock position, which is the closed legs position. This is the open legs position. So this is the demonstration of the walking robot. So as you can see, one part is the 6 o'clock, while the other is the 12 to enable the movement. So once an obstacle is detected, it will reverse itself, and the one side of the leg will lock up, while the other side will continue reversing to complete a 90-degree turn. So for the result of the robot, so we took upon the measurement of the speed of the robot manually. So we indicated the robot to move about 1 meter and recorded the time taken for the robot to reach 1 meter. So we ran the test for 5 times, and the average speed for the average recorded time of the robot is 45.91 seconds, which is equivalent to 0.021 meter per second. And we also tested for the turning speed of the robot to the 90-degree angle. So we ran that for 5 times too. So the average time taken is 13.59 seconds, which is the turning speed in degrees per second is 6.6221 degrees per second. So we also take into account the power consumption under maximum speed of the robot, which is able to be reached by 5.709 for the left and the right, which is equal. So for the conclusion, the robot can walk and detect obstacles and also avoid the obstacles by changing its direction. And then the robot gate is always in phase due to the encoder on the motors. Without the encoders of the motors, if one pair of legs is out of phase, it will be unstable and it will topple over. So for the problems of this prototype, it has a limited degree of freedom, which means it cannot turn very sharply. So it must use the motion I've indicated earlier. So, and then it suffers from slippage on smooth surfaces because the legs is 3D printed. So, and the joints are insecure. We're using entry bolt and nut. So after a few run of the test, the bolt and nut will get locked up and constrict the movement of the robot. So for the future work, we want to enable an out-of-phase stable movement for the curve, for enable of curve path movement. This can be achieved by putting a gear system into the legs. So, and then another type is to attach rubber pads on the legs to decrease the slippage and change the joint connectors with metal rod and bearings because the current connection of the joints is problematic. So that is all. Thank you.
Thank you. Any questions for Harihul? Okay, over to you, Tara.
I have one quick question. So I think you mentioned that you directly use the link length, which is directly specified by JSON work, right?
Yes.
Okay. I think it would be better for you to relook onto the synthesis of the link lengths because the vertical height that your leg takes up, because your end tip of the leg goes through a certain path when the motor is actuated, right?
Yes.
So, and the clearance between your floor and the maximum height that the tip of your leg can take has some kind of a relationship. I think you can just look into, this is just a suggestion that I have. You can just look into the synthesis of the link so that you can adjust that particular parameter. Right now it looks too high. And secondly, yeah, you talked about using one motor for 2 links, right? Are you achieving out of phase by a specific linkage connection between these 2 legs?
Okay, so this is the left side of the robot, right? So okay, this pair of legs is controlled by one motor with an offset of the shaft.
Okay.
It's connected together. Okay, so it is 180 degrees out of phase. So when this one is in the bottom, on the other side is at the top.
Yeah, got it. Yeah, thank you. That is all from me. Good to see Jason's mechanism in your report.
Okay, thank you.
Any other questions?
Excuse me, sir.
Yes, sir. Devanand, sir. Yeah.
What is the strategy for avoiding obstacles that you used?
Sorry?
What is the strategy for avoiding obstacles?
For now, it's just the IR sensors. So currently we put it horizontally, so it can only detect the wall. So later on, if we in the future works, we can adjust the angle to detect a certain height of an obstacle. For now, it's just to detect a wall. Does that answer the question?
Okay. Any other questions? Okay. Thank you. Thank you, Har. You can stop sharing your question.
Thank you, sir.
Yeah, thank you. So we move on to the next paper. We have paper ID 88. So that paper is going to be titled Neural Network Based Inverse Kinematic Solution for a 5 degree of freedom manipulator for industrial application. So with us here we have Aravind Akshan, right? Yeah.
Yeah, yes, sir.
Fine.
Sir, can you let me know if I'm audible and visible?
Yeah, you're audible and visible. You can start projecting.
Okay. So a very good morning to one and all present here. Myself, Aravind Akshan from SR Institute of Technology, hereby presenting.
Can you make your presentation to the full screen mode?
Yes, yes, just hold on. That's what I'm doing. So myself, Aravind Akshan from SR Institute of Technology, hereby present the research paper titled Neural Network Based Inverse Kinematic Solution for a 5 degree freedom manipulator of industrial application. So beginning with the problem statement, in general, planning and control of industrial robots are affected by the method used to solve its inverse kinematics. So it is important for such sector to have the capability to develop a high accurate and efficient solution to the inverse kinematics problem. The complexity of this problem is because of the robot's geometry and the non-linear trigonometric equations that describe the mapping between the Cartesian space and the joint space. Traditional methods such as geometric, numerical, and iterative methods can be used, but becomes complex for higher degree of freedom and they require a longer processing time. And moreover, finding a closed form solution becomes nearly impossible. Therefore, we decided to use neural networks and manipulator to solve the inverse kinematics. We present a pick and place scenario for which we designed a 5 degree of freedom manipulator having RRR-PR configuration. So the basic workflow involved 4 stages, starting with the basic design of manipulator in SolidWorks, the forward kinematics calculation and neural network modeling in MATLAB, and finally simulating the pick and place operation in Simulink. So we have gone with RRR-PR configuration for our study because it has large working space and high mobility. It has very good rigidity in vertical direction and flexibility in horizontal plane. So our manipulator consists of total 5 joints, starting with the revolute joint at the base, a second revolute joint in the shoulder, and the third revolute joint in the elbow, a fourth prismatic joint connecting the upper arm and the forearm, and finally 5th revolute joint in the effector. So these are the design specifications of the robotic arm, where these are the constraints of the robotic arm structures. So we have used Dunawart-Hartenbach parameters and DH frame for calculating the forward kinematics, where figure 3 illustrates the DH frame conventions. And using the transformation matrices, we have calculated the home configuration of end effector, which is described by figure 4 using MATLAB. So moving to the design and setup of neural network, we have designed 2 artificial neural network for a study, where the neural network 1 consists of 3 input parameters, that is the position of end effector along XYZ axis. The neural network 2 consists of position orientation of end effector along XYZ axis. So the neural network was initially tested using 3 different algorithms, that is the Levenberg-McQuadrate, Bayesian regularization, and scale conjugate gradient, from which it was found that the Levenberg algorithm had stopped due to being stuck at local minima. It had poor generalization, and the Bayesian regularization had huge MSE value for train and test data set, leading to poor performance. Finally, the SCG gave a satisfactory result since it's generalized well on the given data. Moving on to the network design criteria, there are total 3 layers in the neural network system. For the first is the input layer, which consists of end effector pose, between a hidden layer, which consists of hidden neurons, and finally an output layer consists of joint variables. The evaluation of performance totally done based on mean square error, where n is the number of samples, yi is the target value, and yi dash is the predicted value from the neural network. Moving on to the neural network training, this is the N1 architecture, where there are 3 input parameters. that is the Px, Vy, Pz, and there are 5 output parameters, that is Q0, Q1, Q2, Q3, and D4. That is the joint variables. In between, the hidden layer has a tan sig model activation function, and the output layer has a linear activation function, where W and B are respective weights and bias of the function. The dataset initially normalized because normalizing the input ensures that our network can effectively learn the parameters on the first layer, since the second layer of the neural network accepts the activation on the first layer. So normalizing these inputs help the network more effectively learn the parameters in the second layer also, and the overall loss function is reduced. Out of the total 1,000 samples, we have used 70% of the sample for training, 20% for the validation, and 10% for testing. So the figure 5 and 6 represent the performance analysis of our NN1 training. Figure 7 is the regression plot, and 8 the error histogram. Basically, first the number of hidden neurons were given as 10, for which the best validation performance stops at epoch 23, giving a good performance level with a mean square value of 1547.55. Then the number of neurons are further varied to achieve a better performance level, and the performance is stopped at epoch 112, giving a low MSE value of 977.72, which is pretty good. And in the regression plot, it can be observed that the basically regression means that it defines the correlation between the targets and outputs, where R value of 1 means it has close relationship and R value of 0 means it has random or poor relationship. Here, the relationship between the target value and output are very good for all the training, testing, and validation data, and the overall regression is obtained is 0.988. Finally, the error histogram, in this bell curve, it can be seen that the larger number of values have an error of 0.1066, meaning which it has treated the joint variables very well. Moving on to the NN2 training, where we have 12 input parameters, that is consist of both end effector, pose, and orientation. First, we have given 10 hidden neurons for our system, for which we have the performance stops at epoch 5, means it has generalized very quickly, giving a poor performance level of around 4000 MSE. Further, a number of neurons are varied to see any improvement in the performance, but the MSE value increases and the performance deteriorates. So from the regression plot, it can be seen that at some point between 0 to 500 samples, it has overfitted the model, and the regression value, it shows a very poor correlation between the targets and outputs. And the overall regression obtained here is 0.92. In this error estimate, you can observe that the most of the values in the samples had an error of minus 3.86, means it is a very high value. And there are several value like minus 40 and minus 50 with a hairy error value between the samples. So moving on to the next slide, these are the training results, where for NN1, the training and testing value are very close to each other, showing that the model has generalized well. Generalization in a neural network is necessary because it shows how good our model is at learning from the given data and applying the learned information elsewhere. If the neural network performs well on the data which it has not trained on, we can say that it is generalized well on the given data set. But whereas for NN2, the testing value is very extremely higher than the training value. It shows it has learned all the data in the training, and it has a poor generalization. And the best validation epochs for NN1 is at 112, and it generalized quickly for NN2. So the table of NN1 and NN2 elaborates the outcome of the neural network. 2 samples of end effector pose from the dataset is introduced to the network. This dataset has a known corresponding value of joint variables, that is the target calculated from the forward kinematics in section 2. The difference between the predicted value and target value are calculated, and a comparison is drawn for NN1 and NN2 systems. So from this, it can be inferred that the NN12 has good prediction than the NN2, since the error is very minimal for NN1, varying from minus 3.8 to 0.6. Whereas for this, we can see the error is around 17 and 17 to 8.5, which is extremely high. So to obtain a better understanding of the performance of the neural network prediction, the trained network is tested on new unseen dataset, which has 300 samples. And the comparison is between the regression values. For NN1, it has very good relation between the outputs and targets. Their value are close to each other and giving a good regression value of 0.98. Whereas for NN2, since the model has been overfit, we can see the regression value as 0.83, which is extremely high. So basically, in a neural network, the number of parameters essentially means the number of weights, which is directly proportional to the number of parameters and the number of layers and the number of neurons in each layer. this. So whenever there is a huge weight in the network, it is very susceptible to small changes, which leads to the input-output variance. So it leads to a degeneration of the neural network. Therefore, it can be concluded that the number of input parameters means if there are more input parameters, more are the chances of overfitting. Hence, it was concluded that NN1 has best prediction over NN2, and that's why the NN1 prediction system has been used for the motion study of robotic arm. Now, finally, moving to the beacon-based simulation part, where the robotics concept model was created in a multi-body simulation environment of robotic arm was carried out. So here we are given 3 waypoints, that is point A, point B, point C, in which it has need to follow the trajectory. Point A is the starting point, point B is the midpoint, in which it reaches the highest velocity, and point C is the goal location, and point A is where the object has been placed. So these values have been given to the NN1 system, and the NN1 system predicts the respective joint variables for each joint that it has to be configured for the end effector. Then they are fed to the partner, and the partner follows a trajectory, and a controlled motion was obtained. So coming to the conclusion part, the inverse kinematics was successfully solved for the neural network. In the prediction, it has very high accuracy prediction and low MSC value for NN1 system. And the neural network can easily identify, map, and predict the complex non-linear behavior and data set, which was impossible for the analytical calculation of inverse kinematics. And drawbacks such as non-trigonometric equations and multiple solutions are overcome. The feature study involves the hardware implementation and the neural network deployment in real time. So this is the basic simulation of the robotic arm motion from point A to point C. Yeah, so these are some references that have been taken for the study. Yes. Hello.
Okay, any questions from audience? Okay, no questions. Okay, over to you, Tiara.
Yeah, thanks for the presentation, Akshay. So my first question is, you chose example of RRR-PR robot, right? Is there any specific reason just to demonstrate this concept, or? The basic reason was that, sir, since the calculating of forward inverse kinematics becomes difficult for different configurations. That is, for RRR, it has simple calculation of inverse kinematics. So we choose RRR-PR because it has a kind of unique configuration, so that the neural network can predict the variables for different kind of configuration. It is impossible. Are you sure there is? Yes, sir. Okay, are you sure there is no inverse kinematic solution for this mechanism? Sir. Because no, sir, there is no inverse kinematic solution. We already checked it, and basically it is a different configuration from the previous configuration, somewhat like that. And basically the solving of inverse kinematics is not possible for different configuration, because there is a problem of singularity, multiple solutions, sometimes solutions are not found. And most of the time we have to use only iterative method, which takes a longer processing time and lot of work. Yeah, I got this. I'm not sure about this comment, because I think there may be a closed loop solution to this mechanism, because it doesn't have any redundant links as such. Yes, sir. Maybe that is something that I have to look into just to make sure. In one research paper which I saw, there was some analytical solution for 5D of robotic arm, which has a different configuration, not for this configuration. Yeah, of course. If you change the mechanism, the solution is going to be completely different. But I think for this particular mechanism, getting a closed loop inverse kinematic solution is not possible. Yeah. A trivial. I don't think, I won't say it is not possible. It takes a lot of computation time, sir, because it is a very hectic task. That's why we use neural networks. No, okay, anyway, so I mean, at least for your comparison, if you can find out what is a closed loop solution, you can just compare, because the argument of proposing this whole neural network approach is to claim that your computation time is less compared to the conventional method. And also, sir, so we don't need to solve it. Argument to compare. Yes, sir, because in the neural network, we can just create data sets and then we can train the neural networks. So it takes around 2 or 3 days, sir, if you sit on this thing. Okay. Another thing, you proposed two neural network schemes, right? NN1
Yes, sir.
and NN2. NN2, I think, from my understanding, from what I understood is you have NN1 just for position tracking and NN2 for orientation also, right?
Yes, sir. Yes, sir.
In
But
a
the
more
thing is,
realistic situation,
yes, sir.
let me complete the question. In a more realistic situation, when you try to use this kind of a manipulation system, you will also have the requirement of orientation also. But
Yes,
when you see in the particular case that you have taken, it is not able to solve for the inverse kinematic solution. I mean, it is solving, but the solution is not accurate.
yes, sir.
Right. So,
So
is there any way to improve it?
yes, sir. Because what we can do is that we can standardize the input parameters. That is, if we are taken in degrees as usual. So if we are taking the values from -1 to 1 or 1 to 0, so that it is similar to the value of the mean square error. So from that view of point, we can see some accuracy, but it requires still some work need to be done in that part.
Okay, because when you talk about higher redundancy robots, then the number of variables will be high. Then the number of neurons again will be high. The number of parameters will be high,
Yes,
and it will again become more complex. The epoch right now is, I think, 5, right? I mean, for the NN2, it stopped at epoch 5, right?
Yeah, because it has not predicted the values well, sir. So we have to use several other neural network method for that.
Okay. Yeah, that is what I was just trying to understand.
Actually, yes, sir. Here we have used a scale conjugate and we have used the MATLAB. If you are going for OpenCV or any other third-party software, with that I think we can make it work for orientation also. But yeah, it requires a lot of time. Yes, sir.
Got it. And final question, you used normalized input, right? So is it just a Cartesian input normalized, or?
Normalized input, Cartesian in the sense that sometimes the values, since you have created a random data set, so there will be some value of degree like -1 and another degree value will be like 45 or 70. So we have changed these values, which is ranging from -1 to this one. The minute value have been changed to values like 40 degree, 35 degree, so that the pick and place operation, when it performs, it has accurate solution for that. Because for some particular locations, it has to need to predict the joint variables. So based on that.
Okay.
Here we have taken 3 waypoints. So for that, we are training the system. Yes, sir.
Did you form any trajectory between these 3 waypoints?
Yes, sir. Yes, sir. Yes, sir. Basically, trajectory you can see is a trapezoidal type trajectory from point A to point C, where in point B it reaches the highest velocity at 90 degree. Then it places the object at point C.
Okay, you chose a trapezoidal trajectory.
Trapezoidal trajectory. Yes, sir. Because it is a time variant and it is very simple. Yeah.
Thank you.
Thank you, sir. Any other questions from the audience?
Okay, thank you, Arvind. Okay.
Yes.
Arvind. So, okay, we have the last paper for today's session. We have Ranjit Pillai with the paper ID of 97. So he is going to present on the topic mechatronics design and kinematic analysis of SMA, spring actuated or parallel manipulator. Over to you, Ranjit.
Yes, sir. Good afternoon, sir. Thank you. Shall I share my screen, sir?
Yeah, please.
Good afternoon, everyone, panel members and respected judges. So today I'll be presenting myself. I'm Ranjit Pillai, working in Assistant Professor in Department of Mechatronics Engineering at SRM Institute of Science and Technology, Katankutur. So I'll be presenting a part of my work, which is mechatronics design and kinematic analysis of SMA spring actuated parallel manipulators. So the content of the presentation is I'll just introduce basically the parallel manipulator, then what is SMA, then the basic design of the manipulator which we have proposed, and the kinematic model, and the preliminary test, because this entire work is just a preliminary analysis of the manipulator, then followed by the conclusion. So parallel manipulators are basically closed loop kinematic chain, which has a base as well as an end effector, where base is stationary and you have an end effector connected with several parallel limbs. So parallel manipulators are better known for its positioning ability because of its better stiffness and because of its inherent closed loop structure. But they suffer from two things. One is the complicated dynamics, because they have a lot of coupled dynamics, and they also suffer from non-linearity in forward kinematics. And when compared to serial manipulators, they have reduced workspace. But in spite of this reduced workspace and complicated dynamics, they are very popular for kind of an simulation platforms, especially when it requires kind of an motion simulation platforms. There is another class of parallel manipulators, which is flexible parallel manipulators. And what makes it flexible? And flexible is popular for unstructured environment, and they are also popular as an additional end effectors. There are many research papers who have used such flexible parallel manipulators as an additional orienting mechanism for a kind of a serial manipulator itself, because this helps to make this better compliance for kind of some peg-in hole or some kind of an insertion applications. And what makes this flexible? There are two constraints which is very important when it comes to flexibility. One is what kind of an actuator we choose, and other is the feedback constraints. Why? Because I cannot put any kind of a stiff sensor, so there should be some kind of an feedback mechanism so that I could have this for the feedback control. I can have this signals. Next is basically the stiffness. So when it comes to parallel manipulator stiffness, two things is like the inherent structural stiffness, and the majority of the stiffness is again accompanied by my actuator. So these are the things which is very important for a flexible parallel manipulator. So in short, so in order to have this flexibility, so use of conventional actuators becomes very difficult to use. So there is again a non-conventional actuators which is popular for such flexible structure. One, we call it as a shape memory alloy. So SMA actuators works on basic principle of crystallographic transformation. When temperature is changed from low temperature to high temperature, it changes its state. And the two states are Martensite state. Martensite is basically the low temperature state where it can be easily deformed. And on heating, it regains back its original shape. That's why it is called a shape memory effect. So hence it works on basically the temperature difference. And in order to have a control, so for example, now as it is dependent on temperature, we use Joule's heating technique where we pass the current, which because of its internal resistance gets converted to temperature and it starts actuating. So the shape memory actuator comes in two forms. One is the wire as well as the spring. So wire has a problem. Why? Because wire, when we use the wire, it has a very limited strain. The strain goes by maximum 5% to the total length. And hence, if you want a larger orientation, you need to have some mechanism in order to amplify the strain. So there are basically many mechanisms involved in literature. One is by mechanical amplification techniques, or second is basically you accommodate more wires in the structure. But this again complicates the entire design. So other is basically use of spring. So in our research, we have used basically a spring, which is a combination of nickel titanium in the percentage of composition percentage of 49-51% procured from Dynaloy, with the wire diameter, spring diameter of 6 mm and wire diameter of 3 mm. But there is again a problem when we use SMA spring. One is the cooling, because the wire we used is of larger diameter, so the cooling time is high and it really accommodates more hysteresis than compared to a wire. So the design which we have here is basically this, where we have this has a parallel structure where we have an end effector and we have a base plate where the end effector and the base plate is connected by a central hinge, which is a universal joint. So inherently, because of the inclusion of the central hinge, universal joint, it really has only 2 degrees of freedom, which my end effector can have, 2 degrees of freedom orientation across X and Y. And 3 SMA springs are connected symmetrically, which is 120 degrees apart as shown here. And these 3 SMA springs provides this 2 degrees of freedom motion. And hence, these are called as redundant parallel manipulators because we use 3 springs to have this 2 degrees of freedom Cartesian. And the plate which we have used is basically acrylic plates, and which are 4 mm width, and the side is it's an equilateral triangular plate which has 100 mm. And these are electrical connectors, and the electrical connectors which hold this SMA springs, and these holds also the wire which passes electric current to these SMA wires. And these are, as this body is completely made by acrylic, so it is completely isolated also. So it is electrically isolated too. So the electronics part involves basically, this is basically the manipulator prototype, which has basically, as I said, these are a universal joint, and this has 3 springs, which electrical connectors. And how really, so entire control algorithm works in this workstation controller in MATLAB Simulink, where the MATLAB Simulink runs this control algorithm. And we have a data acquisition, NI data acquisition device, which holds this input-output cards. And we have a current sensor which measures this current through SMS pin, which is connected to the data acquisition analog input of the data acquisition device, and it has also an analog output module, which supplies sufficient control signal to the current driver, which in turn passes that to the SMA springs. And we use basically in order to measure this orientation of this end effector, we use basically an IME, which measures the orientation of this end effector, which in turn is also used as a feedback element. So we have used an indirect way of measuring this spring length, because the control happens in a way where I need to really control the orientation of this end effector, which in turn is possible because of this SMA actuator position. So in order to measure the SMA actuator position, we use basically this IMU data with the model, which is basically inverse kinematic model, to measure this SMA spring length. So first, in order to understand this kinematic or inverse kinematic model, so the geometric description works in this way, where we have assigned 3 frames: a base frame, which is as this indicated here, X, Y, and Z. And in this universal joint, we have basically 2 length, which is one is the fixed length and one is the distal movable link, and the end effector frame, which is E. So if this joint frame J has 2 degrees of freedom, which is along this X and Y, and the inverse kinematics aims to calculate the desired length for a given orientation. So that means if I have an orientation of my end effector, what is basically the length of my what should be my length of my actuator is what inverse kinematics formulates. And in parallel manipulator, inverse kinematics is very straightforward, which can be done basically using this closed loop kinematic chain. So in general description, this the rotation between basically I have this joint frame, which is here, which is the length L1. So the joint, the rotation, so it has basically a rotation transformation of J with respect to B. So which can be written in terms of rotation of Y into rotation of X, which gives me this. And the other thing is like the distance between this B and E, basically with respect to B, that Z distance can be indicated by basically BJ, and this distance plus JE, where JE is again a fixed distance L2, and this is my L1 distance, where my L2 basically, because this really has this motion, so this length is again dependent. So when you convert to basically base frame, I really require this rotational transformation applied to that. So in short, the Z distance between my end effector, so the end effector with respect to base is given by this matrix. Now, inverse kinematics model, what we basically do is like, in order to find basically this distance di, so I have a distance di which need to be measured. So I use this closed loop chain where so the vector di, if I need to find the vector di, which is ai bi, which is be, so this entire distance be plus ea, this distance ea, and a and b are basically the actuator connecting points, and minus bbi. So which is already found in the previous, which is already written in the previous BBI. So actuator connecting all. So in short, we get basically this, and finding the Euclidean distance gives me basically the length of the actuator. And this inverse kinematics also, the solution of this inverse kinematics also has helped to find the workspace of this proposed manipulator, where what has been done was like the input again is basically theta x and theta y, and what we have done in order to find this x y z, because in general the total transformation of E with respect to B gets a 4x4 matrix, and at the last column of it, which is basically x y z, which is basically indicated by this basically BE. So on iterating between this theta x and theta y, so the entire working range is minus 15 to 15 degrees. So what we have done is like we iterated this for nested for loop and found out basically this x, y, z distance, and we have plotted, and which is basically the workspace of the proposed manipulator is basically this, which we have for which we have used this algorithm. Now, next was basically to understand the preliminary. This was very preliminary over test. So one thing which I said in the introduction itself, finding basically we didn't use any kind of a step sensor for finding this length of the actuator. So a preliminary test was done in 2 ways. One was the open loop test, and next was a closed loop test, which we used just an on-off control just to understand basically the basic dynamics of the manipulator. In this open loop test, first thing which we did was like we used 4 different current limits for 0.5 amps, 1 amps, 1.5, and 2 amps. And what we did was like we just iterated this to different, like that means for 1.5 second, we gave basically 0.4 amps, then 1 amps, 1.5, and 2 amps. And these were given in different springs, combination of different springs, and we measured it physically using vernier, this length of the spring, which is L1, L2, L3, and we measured basically the orientation using the IMU. And this physical measurement, what we did was like we used this model based, the same inverse kinematic model which we used the same orientation fit to find again this L1, L2, L3. So we just compared the physical measurement with the model measurement in order to find out what is basically an average error. Could we use basically that model based feedback for a real control application? And we found like it had an average error approximately less than 0.04 mm. So it really helped us to understand like this can be used where the kinematic model physically works pretty well for a manipulator. Next was just to understand like the time taken, the response of it. So what we did was like we gave a 1 amps current to the actuator till 2 seconds and just wanted to understand the response. And we found like it takes the x-axis, we gave in 2 different axes. So one was to understand like it takes 2 seconds to reach the 10 degrees, but the other axis in 2 seconds it reaches approximately more than 12. So there is some kind of a symmetry in both the axes. So this helped us to understand like even though both the axes are not symmetrical in terms of response, not in terms of geometry, in terms of response. So just an on-off control we'd try to do in order to understand basically the model-based feedback and just to understand the basic dynamics of it. So we use a structure in a way where we maintain 3 volt, which carried basically the driver, so which made a maximum current of 2.2 amps. So what we did was like we first found this basically step response, and we just then did this sinusoidal test. Sinusoidal test was done to understand basically the bandwidth of the system, where we iterated this sinusoidal for 3 different frequencies. One was 0.05. We made a slow test which was 0.05 hertz and 0.1 hertz and 0.2 hertz. And when we increased the frequency beyond 0.2 hertz, it led to basically it was not able to really respond well. So it was somewhat unstable. And in this, one thing which was very important was on increasing the frequency, which you could see basically the initial time it takes, basically the initial gap is higher. This is because these SMAs are really temperature dependent. So it really takes some time to get this activation temperature. So this preliminary test helps us to understand like what could be done in order to shorten this. Even there is even a dynamics part also which comes in. So this can be avoided. This can be reduced using preheating. So in the further studies, what we have done is like for every controller which we have implemented, we have given a kind of a preheating time, where before even the operation we give us preheating, even in a case where it doesn't actuate, but it always is heated up, so that the activation temperature is activation time is reduced, so that this gap is reduced drastically. And out of all these tests, what we found basically is like one is basically the flexible paramanipulator which we used was a simple and a kind of a novel, because the recent manipulator which we used was basically with 4 SMS springs, and this used 3 SMS. But there is a consequence when you use 3 SMS springs. One is like in order to reduce this cross-axis error. So again, that requires a better nonlinear control. So we require a kind of, and again, when it comes to control, the problem here is like SMA are basically a very nonlinear system, where finding a model of such systems is very complicated. So there is always a possible way of finding kind of model-free control. So we have designed a kind of a model-free control as a part of a future work, where we have combined basically something called as fuzzy PID with time delay-based estimation, where time delay-based estimation takes care of the nonlinearities of the SMA, which includes the hysteresis, and the fuzzy part takes care of the error tracking. So we use model free taking into account this because modeling the hysteresis of SMA is really a complicated task, and it has, in order to reduce this cross-axis error, which was found in basically in this open loop test, where we gave for example, when we gave a kind of a circular trajectory which to identify the cross-axis error, it was not able to really respond well to the trajectory, even though it was responding well for individual axes, but it was not able to respond when both the axes were coupled. And also this parameter uncertainties, because which I said basically it depends on Martin-Side and Austin. So there are terms called as Martin-Side fraction, Austin fraction, which are dependent on temperatures. So estimating these requires material characterization. So in order to avoid such material characterization process, it is better like we can go for kind of a model free control approaches. So these were concluded from this preliminary test. So thank you, sir. Any questions?
Okay, let me start with the question for you, Ranjit. Okay.
Yes,
So I have a question. Okay. So since this is a parallel manipulator and you are going for it, since you already suggested there are a lot of non-linearities using this SMA actuator here.
Yes, sir.
My question is why we have to use such a tedious action? We have already established actuators. We are using it normally. So what is your motivation in order to make SMA actuator for this application?
Yes, sir. One was like the larger intention of this work was to use this as an additional orienting device for a, which I've not shown. This was basically an additional orienting device for a tabletop partition robot, small tabletop partition robot. And this requires a kind of an flexibility. So in order to have this flexibility done, that's where we went for kind of an SMA actuators. And if you ask like, why didn't we go for kind of an smart actuator piezoelectric? Again, was like we wanted a larger orientation, which was only possible by the use of such SMA springs.
Orientation and these things is going to be a function of your manipulator design, where in case any additional advantages that like a faster reaction or something that, we are getting it from here. That's what my...
This entire thing doesn't require any faster, sir, because SMA doesn't work fast. So SMA...
Yeah, that's I understand it. That's what my question. SMA is not going to be very fast.
Yes,
in that case, what kind of advantage we can have it rather than going for conventional other actuators, motors and other actuators we have, a lot more other actuators we have. Compared to that, what makes it more advantageous or any way we are going to see that? I'm just curious about it.
Yeah, one is basically when it is used as an additional orienting device. When it is, for example, when it comes to a kind of a peg-in hole or kind of an insertion, it really doesn't require kind of a fast application. One. And secondly is like, sir, like this again is very modular in a way, like when we use kind of a conventional motors, so the stiffness becomes again a challenge for it when you use any conventional actuators. So you don't get kind of this flexibility which need to be attained for certain applications for kind of an unstructured environment.
Okay, thank you, Ranjit. Any other questions from the audience? Okay, over to you, Tyaraj.
Thank you for the presentation, Ranjit. I think it was a very good presentation.
Thank you, sir.
I have actually a lot of questions. First of all, the way you treat the robot. Can you just go to the picture showing the robot?
Yes, sir. Just 1 minute, sir.
Yeah.
Is my screen visible, sir?
Your screen is visible, but I don't see any change. Yeah, I think now you can. Yeah, you can stop. Yeah, okay. So if you see here, to me this looks like a serial manipulator only. I don't look at it as a parallel manipulator. The reason because you have the central link, right?
Yes.
So you can just treat it as one link and then another link mounted on top of this. So if you see in terms of the actual motion, it is actually restricted to the tip of this particular link.
Yes, sir. But these universal joint, if it was active, if it was actuated, then I would have considered that as a serial. But this is again a passive joint, where I have an actuated, because when, for example, I consider Jacobian for this also. When, for example, I consider Jacobian, so there comes basically this passive Jacobian as well as active, where active takes the form of these actuators basically, and with these actuators are connected in parallel.
Still, so I would still say that it is a serial manipulated, actuated using parallel actuators maybe. But see, if you want to track the end of let's say you take the center point of this particular triangle, the top triangle.
Yes.
It will just follow this point, whichever is being tracked. It will be a semicircle, right?
Yes.
I mean, if you consider the whole range, otherwise it will be just a path along the sphere.
Yes.
So, but if you talk about parallel manipulators, and especially with these three are parallel manipulators, then the work volume is completely different. The simplest example is that you can also have a Z translation.
Yes. This is constrained because we have an universal joint, so it constrains basically the Z motion directly, independently. But again, it can be considered even, for example, kind of an spherical manipulators, which you have, which is again a classification of a parallel manipulator, where instead of the universal, you have a spherical joint at the center. But again, you actuate with three or four actuators basically in order to get this spherical work volume. So these are basically passive joints which inherently is used, but there are even, as you said, so there are even kinematics which takes this into account as a serial, and they have even done using the DH, considering like keeping this universal joint intact.
Yeah, because your inverse kinematics model also, it actually proves my argument that the inverse kinematics is quite simple, and that simplicity is basically because you just have these links.
Yes, because
if you imagine you don't have those two links.
Yes, even sir, inverse kinematics are simple even when it comes to parallel manipulator, because you have a kind of a closed loop kinematic chain. Because this itself provides a closed loop kinematic chain.
That is true.
The serial, we don't get this closed loop kinematic chain basically.
Yeah, I mean, it can be advantages or disadvantages because depending on the mechanism of whether it is serial or parallel. I'm not going into that discussion. Okay. My argument is if you don't have the center passive links.
Yes.
The inverse kinematics problem, assuming that you have rigid links in the edges of the triangle, the inverse kinematics problems is completely different. Do you agree with that?
Different. Yes, it's different. Yes, sir.
Yeah, right now to simplify, because you have this passive link, the passive links. I mean, in fact, you can actually ignore the three links which is connecting the edges of the triangle. If you just ignore that, it is as simple as r cos theta and r sin theta.
Yes.
I mean, in your case, it will be r cos theta 1 and r sin theta 1.
Yes.
For one particular degree of freedom.
Yes.
Right, and that is why your inverse kinematics is actually simple.
Simple.
Yeah, so I would recommend you to just look into this, whether you can call this really as a parallel manipulator, that because the community of parallel manipulators, if they see this, they'll actually have the comment whether it is a serial or parallel manipulator. I would partially agree this as a parallel manipulator. I mean, serial manipulator actuated in a parallel sense.
Okay.
So that is fair, but just make sure that this is this falls under the parallel manipulator category. Okay, that is my first thing. And secondly, did you have any kind of a characterization for each of the actuators? I think you presented some results of giving some input.
Yes, our entire research was like, we didn't do any material characterization. So what we did was like, instead of going for a material characterization, because material characterization is a completely different research topic for this SMA, because it requires estimating the material parameters. So our control, which is again kind of a research area where we aimed for going for kind of a model-free approach, where assuming like it was not assumed to be a black box model, where what we understood was like, we know basically the basic characteristics of or specifications of the SMA, and we designed basically the control for which I have not included in this because that was a part of a different research, and we published those work on the fuzzy also, where we designed a error-based fuzzy control, and which we understood like only this error tracking was not able to even compensate the hysteresis. So we combined basically something called as time delay based estimation technique. So which is again kind of an technique which is used to compensate such kind of an hysteresis without using this inverse hysteresis model. So this control was basically to avoid kind of such material characterization in general.
Okay, I mean, so again, the same thing. If you don't have the central links, let us assume you don't have the central links. You are actuating the parallel manipulator just with your SMA actuators.
Yes.
I mean, at least to my understanding, the control is not straightforward, and you're aiming at having a model-free controller, right?
Yes.
It is quite challenging.
Yes.
I'm not sure. I think only after you implement and see, you will be able to guess whether it will be a feasible system or not. But at least to my understanding right now, achieving a model-free controller for that system is not possible. And the simplicity, I mean, you will still be able to achieve this model-free controller having this passive joint. But I think you have to test that.
No, without sir, in this design, I cannot have without this passive joint because these SMS springs are not stiff.
Yeah, I understand that.
Yeah, so bolt too.
Yeah.
Yeah.
Yeah, I understand that. Then again, the argument is it is a serial system, and then you can think of having a model-free controller being in action. And how many states do you have? How many states are you interested in? Are you also interested in the velocities?
No, I have two states, theta x, which is position of main effectors.
Just the positions.
Yes, position of main effectors.
So it becomes like a 2 input, 2 output system. Maybe the inverse kinematic solution is quite straightforward. I think you'll be able to find.
No, sir, 2 input and 3 outputs basically. I have my link 3.
Okay, 3 outputs.
Yeah, it's a redundant.
2 inputs and 3 outputs. Yeah. You have to see. I'm not pretty sure about having a model-free controller for this, but it's quite an interesting work that you're doing. And at any point, if you can try to have this actuator as a black box model, say you have a set of input parameters and set of output parameters, and try to model this as something like a system identification or some other technique to identify.
Yes.
Yeah, if you can do that and try to estimate or try to model the actuator, then you can even think of I don't think you have to really concentrate on model-free control if you can actually model your actuator.
Actually, we tried with the system identification, but the problem with SMA was like this because environment dependency, and again the next problem was like these are again like aging factors. So when, for example, I use the system identification, and for the certain experimental data which I use, if I use it for a different temperature set now, so that model didn't fit well basically. And again, aging matters also because it's aging. So when, for example, I use it for 1,000 trials and next I use, so the response again changes. So these were major constraints, which again was reported in many literatures also, the system identification problems. Where estimating system parameters through experimentally was not as feasible and not as good, like not as responsive, basically. That's where like many literatures are already existing for kind of this model-free control approaches. So that only motivated us. We did the system identification method for we did that. We used ARX model.
Okay. Yeah, and also make sure that your controller. I assume there will be non-linearities in your controller, and you have a multiple input, multiple output system. So 2 inputs and 3 outputs. There's a lot of possibilities that there are some redundant solutions. So I think that is also something that you have to consider. Anyways, overall it is a good work.
Thank you.
Thank you.
Any other questions for Ranjit? Okay, if there is no question, that brings us to the end of this session. I just request Dr. Tyagarajan to just summarize this session. So, and also the request you have to pick a best paper out of this paper, and I'll get back to you and let you know. But we will be announcing that best paper in the validatory function. So I just request you to just summarize the session and conclude.
Sure. Okay. First of all, thank you so much to the organizers for giving me this opportunity, and it was a wonderful session. I also learned a lot from this particular session. There were a lot of interesting work that is being presented, and it was good to see a good amount of research has been taken into taken as a serious job in each of these work. Congratulations to all the presenters for that. And yeah, I mean, it was a good learning experience to me also, being a chair of this particular session. thank you so much again to all the presenters. Yeah, thank you, Saran.
Yeah, thank you very much, Dr. Tyagarajan. I think it's already midnight out there. Okay, so
yeah,
okay, so sparing time with us in the night time due to the time difference and taking up this thing, and it's a very helpful for us. Your help is very appreciated here. So thank you very much
thank
once
you.
again. We have to thank you on behalf of organizing committee. I'll get back to you soon regarding other stuff. So thank you very
Sure,
much.
thank
Yeah.
you.
Okay.
Thank you.
So participants, please join
Thank you.
back us in the Zoom ID 1 in 1 o'clock. We'll have another keynote session starting at 1 o'clock. So we request you to join back by 1 p.m. Thank you everyone. Please.
Thank you, sir.